A very good morning to our esteemed management, to our principal, distinguished speaker, learned faculty members, and my dear students. We are gathered here virtually for an insightful session on the tiny titans of the modern world, semiconductors. On behalf of the Department of Electronics with AI and the Institution Innovation Council, IIC of Sri Chandrababu Jain College, I welcome you all to this webinar. To set the tone for today's proceeding, and I officially welcome our gathering, I invite Dr.S Satya, Head of the Department, Electronics with AI, to deliver the welcome address. Ma'am, the virtual floor is yours.
A warm welcome to our respected Secretary, Sri Lalit Kumar Ujain, respected Principal, Dr. N. Sujata, esteemed Speaker, Dr.S Gomathi, faculty members, and dear students. On behalf of Sri Chandrababu Jain College, we welcome you all the webinar from mobile phone to microchip, understanding the role of semiconductor device. From Alexander Graham Bell, the first telephone, to the smartphone in our hand today. Technology has traveled a remarkable path. At the heart of the revolution lies the silent hero, the semiconductor device. Today, we explore this fascinating journey, how billions of transistors on the semiconductor chip power the device we use every day. We are privileged to have Dr. S. Gomathi, Associate Professor, St.Peter's Institute of Higher Education and Research, with us to reveal the science and engineering behind it. I welcome you all to an engaging section of learning and curiosity. Thank you, ma'am.
Thank you, Dr. Satya, for those warm words of welcome and for highlighting the significance of today's topic in the evolving landscape of artificial intelligence and electronics. Our session today is graced by a truly distinguished academician whose expertise will surely illuminate our understanding of microchips and integrated circuits. To formally introduce our chief guest, I now call upon Dr. I. Sivagami, Assistant Professor, EAI Department. Please, ma'am.
Good morning, everyone. It's my privilege to introduce our distinguished speaker for today's webinar, Dr. S. Gomathi, Associate Professor of Physics at St. Peter's Institute of Higher Education and Research, Chennai. Dr. Gomathi brings with her over 19 years of rich teaching experience in the field of physics and has made remarkable contribution in academics and research. She earned her PhD in physics from University of Madras and has specialized expertise in solid-state physics, quantum mechanics, spectroscopy, nuclear physics, and computational physics. She has published 12 research papers in international journals, and her research interests include crystallography, molecular docking, Hirschfield analysis, and green nanotechnology. In addition to her academic excellence, she has served as a university examiner, paper setter, evaluator, organized national conferences and workshops, completed NPTEL courses, and is currently guiding PhD scholars and postgraduate students. Today, we are honored to have such an accomplished academician with us to share her valuable insights. On behalf of our institutions, I warmly welcome Dr. S. Gomathi ma'am and thank her for joining us today. Thank you.
Thank you, Dr. Sivagami. We are indeed honored to have such an eminent personality with us today. I now request our chief guest to take over the session and lead us through this fascinating journey.
Good morning, everyone. Thank you for the insightful address, ma'am. I would like to thank the management, principal, and head of the Department of Electronics with AI for giving me this opportunity. Once again, thank you. I warmly welcome you to the today webinar on from mobile phone to microchips, the role of semiconductor devices. Can I share my PPT, ma'am?
Yes, ma'am, you can.
Let me begin with a simple question. Can you imagine a day without your mobile phone? Just think for a moment. From waking up in the morning to making calls and using social media, making payments, everything depend on this small device. But have you ever thought what makes this small device so powerful? Inside this mobile phone, there are million to billions of
Excuse me,
tiny components. Ma'am?
ma'am. You haven't shared your screen yet.
Okay, one second. Screen is visible.
No, ma'am.
No, ma'am.
The presentation is not visible.
Presentation not visible. Once again. Once again. Once again, ma'am.
It's okay, ma'am. Take your time.
Maka. Okay, sorry for the intro. Okay. So now, uh, so see, let me begin with this simple question. So no need to answer. So can you imagine a day without your mobile phone? Just think for a moment. From waking up in the morning, making calls, using social medias, making payments, everything depend on this small device. But have you ever wondered what makes this small device so powerful? Inside this mobile phone, there are million to billions of tiny components working together. and most of them are based on one important concept, that is semiconductors. So, which are the building blocks of modern electronics. In today's section, we discuss the basics of first we understand the basics of concepts of semiconductors, then we will see how the semiconductor devices are formed and work, and finally we will connect all this concept to real component inside a mobile phone. So first, let us start with the basic concept, a semiconductor. So a semiconductor is a material whose conductivity is lies between conductors and insulators. For the example of the conductors like copper allows current to flow easily, insulators like rubber block current completely, but semiconductors behaves in between. Common semiconductor materials are include silicon and germanium. The most important property is we can control the conductivity of semiconductors by changing the temperature. So when we adding the impurities or applying the voltage. So this control ability makes them extremely useful. So let me explain this concept with a simple real life example. So imagine a road. If the road is completely free, vehicles can move smoothly without any interruption. So this is similar to a conductor. So the electrons move freely in a conductor. If the road is completely blocked, so the vehicle cannot move at all. So this is similar to like a insulator. So now imagine a traffic signal. So when the signal is red, vehicles stop. When it turns green, vehicles move. So this is exactly how a semiconductor behaves. So we can control the movement, or in this case, we can control the flow of current. So let me move on to the energy band concept. So inside a semiconductors, electrons occupy specific energy levels called bands. So there are two important bands. So see in these pictures, there are two bands. One is valence band. So here the electrons are tightly bound. In the conduction band where the electrons can move freely. Between these two bands, there is a small gap that is called as forbidden energy gap. So when the energy is supplied, such as like when we apply increase the temperature or when we apply the voltage, the electrons gain energy. So the electron gain the energy and jump from valence band to the conduction band. Once this electron reach the conduction band, they can move freely and they start to conduct electricity. So in semiconductors, the current is carried by two types of charge carriers. So here one is electron, so which are negatively charged particles. Another one is holes, which behave like positive charge. So when an electron moves from the valence band, it creates a vacancy. So that is called as hole. So in semiconductor, both electrons and holes contribute to current flow. This dual contributions mechanism is a unique feature of a semiconductors. So now let us look at intrinsic semiconductor. So an intrinsic semiconductor is a pure semiconductor without any impurities. So in this case, the number of electrons which is equal to the number of volts. So the conductivity of intrinsic semiconductor is very low. So at the room temperature, initially the room temperature, the uh, intrinsic semiconductor only a small number of electrons have enough energy to move into the conduction band. So the intrinsic semiconductor are not very efficient for practical applications. So now we show that intrinsic semiconductor are pure, but their conductivity is very low. So they are not very useful in real applications. So what do we do? So we improve their conductivity by adding a very small amount of impurity. And this process is called as doping. Because pure silicon has very few free electrons, so we need to increase the number of charge carriers. First, the n-type semiconductor. Here we have the pentavalent atom like phosphorus, arsenic, antimony. These are the example for pentavalent atom. So this atom have 5 electrons in their outer shell, but silicon needs only 4 electron for bonding. So one extra electron become free. So this free electron can move easily. So the conductivity increase. So that's why we say in n-type semiconductor, electrons are the majority carriers. So now we see p-type semiconductors. So here we add the trivalent atom like boron. So this atom have only 3 electrons. So one bond is incomplete. So this creates a hole. So this hole behaves like a positive charge. So now current can flow through hole movement. So in n-type semiconductors, holes are the majority carriers. So now by doping, we can control the number of charge carriers, and this is the first step in making the semiconductor devices. Now comes the most important concept, that is PN junction. What happens if we join p-type and n-type together? So we get a PN junction. When they are joined, electrons from n side move to the p side, holes from p side and move to n side. So they combine and cancel each other. So near the junction, there are no free electrons or holes left. So this region is called depletion region. This region acts as a barrier, like a barrier. It does not allow the current to flow easily through the material. So initially the PN junction behaves like an insulator. So this PN junction is the foundation of all semiconductor devices such as diode, transistors, integrated circuits, everything start from here. So if the PN junction blocks current, how do we make it conduct? We apply an external voltage, that is called biasing. So in forward bias, the positive terminal of the battery is connected to the P side of the material, and the negative terminal of the battery is connected to the N side. Now what happens? The barrier become weak. So the depletion region becomes very thin or narrow. So the electrons cross the junction and current flows easily. But in reverse case, the positive terminal is connected to the N side and the negative terminal is connected into the P side. So now the barrier becomes stronger. So the depletion region becomes very wider. So no current flows. So by changing the voltage, we can control current flow. So this is the basic idea behind the switching device. So let us see a real device, a diode. A diode is simply a PN junctions. So in diode, the forward bias, when we apply the forward bias, the current flow through the circuits. So in reverse bias, the current is blocked. So the diode allows current only in one direction. So this is one way property is very useful. So this is the diagram, schematic diagram for the PN junction diode. So the SMD diode. For example, in your mobile charger, the alternating current supply is converted into direct current using diodes. So this diode also used in power supplies, signal processing and protection circuits. So yes, simply we can say the PN junction becomes a powerful device called diode. And this is used in almost every electronic circuit. Now, now we have understood diode. So next we will move to more advanced device like transistor. So a transistor can act as a switch or an amplifier. In modern electronics, we use MOSFET which are very efficient, so they are very fast, consume less power and highly reliable. So inside the microchips, there are billions of these tiny transistors. Now let us connect all these concepts to real life. When you open your mobile phone motherboard, you will see many tiny components. So these are called as surface mount device, that is SMDs. So they are very small but perform very important functions. So the first one is the processor. The processor is the brain of the phone. It contains billions of transistors. Each transistor works as a switch, processing digital signals. All operations like running apps, calls, games are handled here. Memory chips. So these store your data. So the memory chip store your data. They are also built using semiconductor device. They help in storing and retrieving the information very quickly. So you will see the tiny components around the chip resistors. So these resistors control the current. The capacitor, it can used to store the energy. Diodes, it control directions. So even though they are small, they are essential for circuit operations. The next one is the power management system. So that is a special chip called PMIC, controls power. So this power management ICs manages battery charging, voltage supply and heat control. So this ensures safe and efficient operations. The another one is display systems. So your mobile screen is made up of semiconductor materials. Each pixels emit light when the current passes through it. So that's how images and videos are displayed. So in your mobile phone, many sensors are inbuilt. So the sensors, the camera uses semiconductors sensors. It converts the light into electrical signals which are processed into images. So your phone communicate using semiconductor chips. They handle signal transmission, signal reception, and data processing. So from the smallest SMD components to the processor, everything in your mobile phone is based on semiconductor. All the components are integrated into a single chip called an integrated circuits. Billions or millions or billions of devices are packed into a tiny area. This is what makes modern electronics compact and powerful. So let us conclude. The semiconductors are the foundation of modern technology. From basic material to complex devices, they play a crucial role in every electronic system. Mobile phones are the best example of how semiconductor physics is applied in real life. Thank you for the attention. I hope you clearly understood both the concept and its application. So next time when you see your mobile phone, remember billions of semiconductor devices are working silently inside it.
Thank you, ma'am, for the wonderful session. As we draw this intellectually stimulating webinar to a close, it is time to express our gratitude to everyone who made this event possible. I invite Mr. M. Kumaresan, Assistant Professor, EI Department, to propose the vote of thanks.
Thank you, ma'am. Good morning, everyone to present here. On behalf of the Department of Electronics with Artificial Intelligence, associated with the IIC, Sri Chandraprabhu Jain College, I take this opportunity to propose the vote of thanks for today's webinar program. First and foremost, I express my heartfelt gratitude to our esteemed resource person, Dr.S Gomathi, Associate Professor, St. Peter's Institute of Higher Education and Research. Ma'am, your section was excellent. It gave you an ideas and creative thinking and truly enlightening. Thank you for taking your valuable time to be with us today. I sincerely thank our Secretary Sri Lalit Kumar Jain for his constant support and encouragement in organizing such academic initiatives. My deep gratitude to our principal, Dr. N. Sujata ma'am, for her guidance and motivations that made this webinar possible. I also extend my sincere thanks to all the heads of various departments, faculty members, technical teams, and my dear students for this coordination to organize the program in successful manner. Once again, thank you to all.
Thank you, Mr. Kumaresan. With this, we conclude our webinar. Stay safe and keep learning. Have a wonderful day ahead.